$200, I'm sure that book would be like $5.
Yeah. But this way, by switching to Cengage Unlimited, anyone taking one of my classes, whether it's physics, trig, statistics, any of my classes, they'll buy the Cengage Unlimited, and they're covered for all of them for a year. And I think there's also an option to buy it for just one semester, but I can't imagine why you would. All right. We left off last time with electric power. Anybody else want to turn in homework? Anybody want to ask questions about homework? Nope and nope. Excellent. All right. We talked about power. And power is voltage times current. Watts. It is energy per unit time, or joules per second. We saw that volts are what? Joules per coulomb. So you can divide the voltage what was the example we did? It was the lightning bolt. Yeah, that's it. Where we divided the change in potential, the voltage difference, by the we divided the change in potential energy, which was joules, by voltage, which is joules per coulomb, to find the total amount of charge that was transferred in a lightning strike. Yeah. And in section 6, we looked at power in household circuits, asking, when will the breaker flip? I don't know if any of y'all have ever had this experience. I know we've had it happen here a couple of times when the chemistry department fires up one too many heaters at a time, or they plug in one too many things on one branch of a circuit and pops the circuit, and we have to call the building maintenance people to send someone out to flip the breaker back on. We have a circuit at my house where we had this old microwave that's plugged into in the kitchen that happened to be the same circuit as the receptacle on the island where I'd plug in the kettle for heating water to make my coffee. And it turned out that if I was running that microwave at full power and somebody turned on the kettle, that was enough to trip the breaker. They'd both go dead. We'd have to go with the breaker back on. Of course, breakers are specified how? You look on your electrical multi-breaker panel. How are the breakers specified? By how much current it takes to trip it. If it's a 20 amp breaker, then it'll handle 20 amps. If you go over 20 amps, boom, it trips. Well, you add, you look at how all the receptacles on that circuit are all wired in parallel, and you've got one, in my case, I've got a 20 amp breaker, and I've got a kettle drawing 3 amps, and a microwave drawing another 15 amps, and something else drawing a couple of amps somewhere else. Boom. Trips the breaker. Do we need to go and look any more closely at how to calculate the total current flowing in a circuit? If everything's in parallel, if everything's in series. Seriously, if anybody not clear on that? Yeah. Okay. Well, and don't forget tomorrow, those of you who have it, make sure you have your laptop or tablet or notebook or whatever you've got with your circuit simulation software on it. Because those of you who don't are going to get to use some state-of-the-art 1980s Macintosh technology. to do your lab tomorrow. That's fine. I'll get a couple of them fired up. Huh? Does it do circuit simulation where you can build a circuit with resistors and switches and power supplies, and it'll tell you how much voltage is dropped here and how much current is flowing there? That's what you're going to need. Let's now look at alternating current. Alternating current. If I'm graphing current as a function of time, and it does this, is that an alternating current or a direct current? And this is a trick question. It would be, but can you tell me why? Because it never changes and goes the other direction. It goes higher in one direction and lower in the same direction, and it's fluctuating. This is a highly not stable, this is not a steady state current by any stretch of your wildest drug-induced hallucinations. But it is DC, it is not AC, because it never goes negative. An alternating current is one that flows in one direction for a time, and then it flows in the opposite direction for a time. So, let's draw a proper alternating current. And it looks like that. Now it's going positive. It reaches some peak value. It goes back to 0. And then it goes to its negative peak value. Back to 0 and so forth. Now, we're not dealing with reactive circuits yet, so this is purely a resistive circuit we're talking about. Okay, if that means anything to you. In other words, there's no capacitors, no inductors, it's strictly resistor. So there's no phase shifting of anything. What would the voltage look like that was associated with that current? Because it's a purely resistive circuit, there's no capacitors, no inductors. The voltage and the current are in phase. When the voltage is at peak voltage, divided by its peak current, that would tell you the resistance. Am I getting that right? I equals E over R. R equals E over I, yeah. So you divide this peak voltage by this peak current, and that gives you the value of the resistance of that circuit. As the voltage drops to 0, 0 divided by that same resistance gives you 0 current. The negative voltage peak divided by that resistance gives you a negative current. Now, what's the power in this circuit? Well, the power here this current times that voltage gives you that much power. Peak power. But that's how much power is being dissipated, being developed in that current circuit at that moment in time. How much power is being developed right there where there's 0 volts and 0 current, 0 power. So your power looks like that. What about here? How much power is being developed here? No. A negative power would mean you're pumping energy into the, or you're taking energy out of this. A negative power wouldn't make a whole lot of sense, would it? A negative voltage times a negative current means there's your power here for this half cycle. And again for this half cycle. So, the power is not steady state, but the power is always positive. Now, what's the average power there? Yeah. Here's from 0 to pi to 2 pi. So if you were going to go from, well, if you're going to take the average power from 0 to pi, it would be the integral of that cycle divided by that distance, by pi, which is, that's 0, that's pi, that's 2 pi, 3 pi. So it would be the integral of that power divided by that distance, which is pi, minus 0, which is pi. But how would you write that in terms of voltage and current? What's the average voltage from 0 to 2 pi? It's the average voltage. Where did the red one go? There it is. The average voltage is something like this. So it's this much minus that much. The voltage, when you integrate that whole sequence, for every moment that it's positive, it spends a moment negative. So it averages out to 0. Now, is your average power going to average out to 0? No, because there's no negative power. It's always going to be positive. This is why we deal with what's called the root mean square. This is where RMS comes from. What you're basically doing is squaring the voltage or the current and then taking the average of that. Okay? Now, if we write the equation of that voltage, as a function of time, or whatever, it's going to be at peak voltage times the sine of omega t. Right? So, if you integrate sine of omega t from 0 to 2 pi, it's going to integrate to 0. You're going to to spend half the time positive, half the time negative, it goes to 0. The same thing would be true if we looked at the current. It's the peak current times sine of omega t. But what's the average power? Power as a function of time is equal to peak voltage times sine omega t times peak current times sine omega t, which is equal to the voltage times the current times sine squared omega t. See what just happened? As soon as you square that sine function, it stays positive on both halves of the cycle. Now, if you want the average, then you just integrate and divide by the range, which in this case is 2 pi minus 0, or just 2 pi. So it becomes 1 over 2 pi times peak voltage times peak current times the integral from 0 to 2 pi of sine squared omega t d omega t. Or we can just call it omega t, we can just change that to x. I'm dividing it by 2 pi, so I pulled that out to here. 1 over 2 pi out front. How many of you have had calculus? Okay. Yeah, just pull out the constants. Voltage peak doesn't change with time. Neither does peak current. Neither does 2 pi. Yeah, well, technically this is not a calculus-based physics course, so yeah. This is not going to be something on any of your tests, but I still want you to understand what's going on and why. Right. Where we just made the substitution, x is omega t. We can go through and do the calculation here, but the bottom line is you get your table of integrals and look it up, and you're going to find that the integral of sine squared x dx is going to be, this will equal 1 over 2 pi Vp Ip times x over 2 minus sine of 2x over 4, evaluated from 0 to 2 pi. Okay, well, that means you write, make more room here. That becomes 1 over 2 pi Vp Ip times 2 pi over 2 minus sine of 2 pi times 2. What's sine of 2 pi or any multiple of 2 pi? 0. So it's minus 0 over 4. Then minus the same thing evaluated at 0, which would be minus 0 over 2 minus a negative, so plus sine of 0 over 4. And sine of 0 is, again, 0 over 4. So this whole thing comes out to 2 pi over 2 peak voltage times peak current divided by 2 pi times 2 pi over 2, where the 2 pi's cancel, and you're left with Vp Ip over 2 is your average power. Now, notice here, we can also write this as Vp times Ip over the square root of 2 in both cases. All right. See what happened there? Does this look familiar? Peak voltage divided by the square root of 2 is what? That's your RMS voltage. VRMS, root mean square, is peak voltage divided by the square root of 2. What's the square root of 2? 1.4, 1 something something, and you take 1 over that and you get 0.707. RMS current is your peak current divided by the square root of 2. So your average power is simply your RMS voltage times your RMS current. That's why we use RMS instead of peak or peak to peak or whatever other ways you want to develop. Okay? You could do this same thing if we just looked at analyzing the average voltage over a 2 pi over one full period. The average voltage would work out to the peak voltage divided by the square root of 2 over one full period. Same with the current. If you just analyze the current, put the average current over a get the same thing. Of course, you'd have to take the average, the square root of the average current squared. But this is the most straightforward way to get there from here, so you can see where the RMS values come from. It has to do, it's all about recognizing that just because the voltage and the current go negative doesn't mean the power goes negative. And so even when an alternating current is, even when you have an alternating current, whether the current is flowing one direction or the other, it doesn't matter. The power is going to still dissipate the same amount of power. It's still going to expend the same amount of energy. Any questions about this? Well, that was painless. Okay, there is one more here. Talking about the speed of an electron in a wire. Before we do go on, we'll touch base on this. I want to make sure y'all both understand. Do you notice that at no time did we talk about the RMS power? There is no RMS power. Power is just the average power. Okay, the instantaneous power at any moment that's being developed in the circuit represented by this voltage and current. The instantaneous power at any moment is just that, the product of the voltage and the current at that moment, at that instant. So, and it varies from 0 to its peak value, which is the peak voltage times the peak current. So we can talk about peak power, and we can talk about average power, but there is no RMS power. Right? Now, you'll notice at no time did we take the square root of the power to get back to the average power. If you want to talk about the average voltage, you have to calculate the average of the voltage squared and then take the square root of it. And that's why you get a root mean square. You don't get a root square of the power at any point. Okay? How fast do you think electrons move in a wire? We got wires in the walls with electrons flowing through them up in the ceiling, going lighting. I think so, huh? What about you? How fast do you think those electrons move? Would you be shocked? I really did not intend to pun there. In fact, that's embarrassing. Let's just rewind and pretend like I didn't say that. Would you be surprised to find out that the electrons moving through that wire, making those lights come on, are actually moving probably about maybe as fast as, or not quite as fast as you would just walk? It is surprising because people think of electricity as, the speed of light. Something super fast. It's just instantaneous. It doesn't take time. You touch that live wire on that electric fence, you don't have to wait for the electrons to make their way from the thing over to where you're at and start hitting you. You don't have to wait for it. It's boom, right now. But they actually aren't that fast. It's the voltage, the E field, and the potential that propagate at the speed of light along a conductor. The current, the actual electron speed themselves, not so fast. You literally outrun them just by walking. You wouldn't even have to work up a sweat. I mean, even I, middle-aged fat man, no problem. I can just stroll along, keep right up with them. Do y'all ever do any printed circuit boards, work with high-speed digital electronics? Yeah? That's a good question. High-speed digital electronics means where the voltage changes very, very fast. Y'all do printed circuit boards, digital electronics? Okay. And so y'all did not, but y'all haven't done any circuit board design, anything? Okay. If you ever do any printed circuit design, you're going to find that there is a branch, a section, there's a whole field of circuit design called high-speed digital electronics. That people who, the designers who design regular circuit boards just consider it all black magic voodoo and they don't fool with it. It's like, nope, and seriously, you start trying to put together a digital circuit, microprocessor, microcontroller, PLCs, those circuits can just really climb up your pants legs and bite you in the backside. When I was doing my doctoral thesis, I built a mass spectrometer that ion trapped, and one of the last developments I made on it was I converted it from analog controls to digital computer interface controls. And that meant designing a digital circuit board to control it, everything, and it worked beautifully, except for one setting on one of the controls. And when I would set this one particular parameter to a certain value, the whole thing would just go and didn't work. It just died, shut down right there. It's like, nope, not going to play. Now I changed that value to any other value and everything worked great. But it was like at that one setting, it wouldn't work. Well, it's because when you have a voltage in digital electronics, digital circuits, your voltage, there are no intermediate voltage states. It's either zero or high. Okay? Or in some cases like, I don't know if y'all even still, well, you still use, do y'all still use USB protocols? Okay, on USB, it's either plus D or negative D. It's plus or minus a voltage. Same thing would be true on the old UART, where it's either plus 12 or minus 12. It's never anywhere in between. TTL, which, do y'all know what TTL stands for? Say again? No, transistor. Yeah, no, it's, I understand, no. TTL means transistor logic. And it stems back into the old days, back in the 60s and 70s, when they would make an inverter out of just transistor logic. Or they would do an AND gate, or an OR gate, or an exclusive AND gate, all these logic gates. They would actually build them out of transistors. Yeah. Yeah, when I was teaching electronics back in the 89 and 90, shut up. When I was teaching electronics, that was one of the things I had them do. Is I had them actually go in with actual three-legged NPN, PNP transistors, build logic circuits. Build an inverter. Now take that inverter and connect some more of it together and make an AND gate. And actually build them out of transistors on a little breadboard. At any rate, when that voltage changes state, it doesn't happen instantly. There is no discontinuity in the circuit. It takes a certain amount of time for the voltage to go from, say, 5 volts, or nowadays it's 3 volts, down to 0. And it may take a few nanoseconds for it to happen, but it takes 5 to 15 nanoseconds for the voltage to change from one state to the next. Well, 15 nanoseconds is a long time for something moving at the speed of light. That electric field, that potential gradient, it propagates along that conductor, does so at the speed of light, or something very close to it, depending on the dielectric constants. That means that in 1 nanosecond, that voltage is going to propagate about, depending on the substrate material, dielectric constants, and so forth. It's going to travel about between 6 and 8 inches, maybe 11 inches per nanosecond. Full speed of light is basically just under a foot per nanosecond. 11 inches, 12 inches, something like that. Well, you put in dielectric constants and stuff, and it slows it down. It goes from 11, 12 inches down to 6, 7, 8 inches. Well, if you've got a voltage that's transitioning in, say it takes 15 nanoseconds or 5 nanoseconds, well, that means it's going to take, if that has to propagate, 24 inches, and on some of these old backplanes that they used to put in these big servers and memory arrays and things, you could have traces that were 24, 36, 48 inches long with no problem. Well, you change the voltage from 3 volts to 0 volts at one end, and it takes, if it takes 15 nanoseconds for that to happen, well, that means that if the other end of that trace is 15 inches away, then there is a time when that one conductor has 2 different potentials, 2 different voltages at both ends. And when that starts happening, now you have to start treating it not as a steady state voltage, you have to treat it as a wave, a plane wave propagating. It means you have to match impedances and keep it balanced and make sure that when it gets to the other end, it's going to hit a load that has the same impedance, so it will transfer to the load and not reflect back. Not, because if it's an impedance imbalance or a mismatch at a terminal point somewhere, that signal will just reflect right straight back on itself. I don't know if any of you have ever done any radio communications, or speaking, or transceivers. Did you ever put a CB radio in your car? What's the last thing you had to do when you mounted it? You hooked up the antenna. The first thing before you keyed the microphone to test it, you checked your SWR, standing wave ratio, because if that was imbalanced, that antenna was imbalanced to that transmitter, that signal would shoot out that coax, hit that antenna, and reflect right back into the CB radio and fry the whole thing. It gets pretty nasty. It can get pretty nasty. It can get really hairy, and it does get rather complex. But it all stems from the fact that nothing happens instantaneously. And it takes time for a potential or an E field to propagate along a conductor. But once that E field does propagate the length of that conductor, the electrons that are being accelerated and are being pushed and moving, they're not really going that fast. They're bouncing from one atom to the next. And here in 1808, they go through a derivation of how it's called the drift velocity of electrons. So rather than try and, let's just read through it together and see if we can make sense of it. It can be useful to analyze a simple model of electric current at the microscopic level of atoms and electrons. In a conducting wire, for example, we can imagine the free electrons as moving about randomly at high speeds, bouncing off the atoms of an electric field, bouncing off the atoms of the wire, somewhat like the molecules of a gas. When an electric field exists in the wire, the electrons feel a force and initially begin to accelerate. But they soon reach a more steady average velocity known as their drift velocity. Collisions with atoms in the wire keep them from accelerating further. That's the main force at work here. There are 2 forces. There's the force of the E field accelerating the electrons, and we've studied that in the vacuum, where you talk about an electron being accelerated across a potential difference, picks up so many eV of energy, which you convert to joules, which you can then calculate 1/2 mv squared, and find the velocity of that electron. But that's in a vacuum, where there's nothing for it to run into. You put that same electron in a wire, it's now having to make its way through a lattice of copper atoms. And that means that there is a distance, an average distance it's going to travel before it collides with one of those atoms and gets kicked, bounces back in the other direction, or bounces off to one side, or and every collision it's going to take off in some some random direction. The drift velocity is normally very much smaller than the electron's average random speed. And that is what we tend to think of as the speed of the electron. And between atoms, its speed would probably be fairly significant. We can relate the drift velocity to the macroscopic current I in the wire. In a time delta t, the electrons will travel a distance L equals drift velocity times delta t. Length equals rate times time. Now suppose the wire has a cross-sectional area A. Then in time delta t, electrons in a volume V, which is equal to the cross-sectional area times the length L, which is equal to the cross-sectional area times the drift velocity times that delta t, will pass through the cross-section area of the wire, as shown in figure 1825. Now, if there are n free electrons, each with a magnitude of charge E per unit volume, then the total charge, the total number of electrons is n equals n times V, where V is a volume, not a voltage. And the total charge delta Q that passes through the area in a time delta T is the total number of charges n times the charge per particle, which is n times the volume times E, the charge E, which is n times the cross-sectional area times the drift velocity times delta T times the charge E. Therefore, the magnitude of the current I in the wire is delta Q per delta T, which is equal to the N times the charge E times the cross-sectional area times the drift velocity of the wire. Does that make sense to any of you? Let's see if we can step through this. We're looking at, we've already in fact looked at how many electrons have to pass a given point in a wire through one cross-sectional plane of the wire, A, every second in order to constitute 1 amp. That would be what? 6.24 times 10 to the power of 18 electrons, where each one of them is 1.6022 times 10 to the minus 19 coulombs, giving you 1 coulomb per second passing through that point in the wire. Okay. How far will that electron travel? boy. Let's start over and write this down. We're going to relate the drift velocity, V sub d, and that is V sub d, not Vd. Okay. Don't even get that, did you? No? Never mind. The drift velocity to the macroscopic current I, where I is delta Q per unit time. Delta Q divided by delta T. Now, in a time delta T, the electrons are going to travel that distance, L. Okay, they're drifting this fast for this long. That's how far they move. Okay? Now, if the wire has a cross-sectional area A, then in this amount of time, delta T, the electrons in that volume of wire will be A times L. That's the amount of electrons which itself is equal to, L is equal to cross-sectional area times drift velocity times delta T. That gives you the volume, that little chunk of volume, V, which is a volume, not a voltage. Yeah, this is a V. But this is a volume, not a voltage. Okay? And it's the cross-sectional area times the length, which is the drift velocity times delta T. So in that delta T, number of electrons will pass, the electrons in this volume of wire will pass through this plane of the wire. However many are in that volume, in that unit time delta T, in that amount of time delta T, that many are going to pass through that plane. See what I'm saying? This length represents drift velocity times delta T. So however many electrons are in that volume of wire, in that amount of time, delta T, that's how many electrons are going to pass through that one end of the plane, at one point in the wire. Everybody understand that? Okay. Now, if there are the number of free electrons there are N free electrons in that unit of volume, and each of them has a charge E, the charge of an electron, which is 1.6 1.6022 times 10 to the minus 19 coulomb. Then the total number of electrons in that volume, if this is the number of free electrons per unit volume, then the total number of electrons in that unit, in that chunk of wire, is going to be equal to N, which is lowercase n, the number of free electrons per unit volume, times that volume. Okay? And if each one of those electrons has a charge E, then the total charge in that unit volume, Q in that volume, is going to be equal to N times the volume, not the voltage, the volume, times E, where E is 1.6022 times 10 to the minus 19 coulombs. So, that means we now have a total delta charge in that volume, which is equal to N times the volume times E, where the volume is the area times the drift velocity times delta T, and all of that times E. That is the total charge in this volume, which is L long, where L is drift velocity times delta T. Now, if we talk about the change in current per delta T per unit time, that is simply our actual current, coulombs per second. So if we divide that by time, by the delta T, we end up with an equation for our current flowing in the wire of N times the area, the cross-sectional area of the wire, N being the number of free electrons per unit volume in that conductive material, cross-sectional area of the conductor, times the drift velocity of the electrons, times E, which I'm just going to put in 1.6022 times 10 to the minus 19 coulombs, the charge of one electron. Okay? Technically, that should be a negative, but you get the idea. If we know the current in a wire, and we know the cross-sectional area of the wire, then the only thing we need to know at that point is what is the average number of free electrons per unit volume of that conductive material. And we can then calculate and solve for the average drift velocity of those electrons as they, we know that there's going to be some net positive gain, but it's not going to be all in one shot. They're going to move forward, they're going to zip forward, bounce backwards, bounce up and down, sideways, frontwards and backwards, so that as that electron starts migrating through that wire, it's going to hit, bounce, 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 bounce. It's going to take this incredibly circuitous path to get to the other end. In this example, they tell us that atomic mass of copper is 63 U. And so they end up with 6.02 times 10 to the power of 23 free electrons per volume. And I see that we're out of time. But in this case, they look and they calculate out that in a copper wire at 5 amps, the average drift velocity of those electrons migrating through that wire, only about 0.05 millimeters. Just like 5% of 1 millimeter. Or 5/100,000ths of a meter per second. Like I said, incredibly slow. Any of us could outwalk them. Walk much, much faster than that. And I know we're out of time, but I do believe that there's at least one homework assignment, one homework problem where that's going to be an issue. So, any questions, comments, thoughts? We'll see y'all tomorrow for lab.